into the application basically of what we learned for making energy materials, and especially today will be processing of energy materials that we're going to talk about, yeah? So, there's a whole variety of materials out there, of course, that are used in energy. So if you think of wind turbines, nuclear power stations, membranes, basically polymers for using sailing gradients. There's a large part of materials actually in the field of metals and ceramics that are basically associated with this. And with this group of metals and ceramics, there is processing route is typically particulate based. Particles, especially for ceramics, is obvious. You can't melt these compounds, so you have to actually process them at a lower temperature before they melt. And that's why you start with particles and then use the sintering process in there. So in one example we're going to use today, because it shows the complexity of basically the older production and then make it more environmentally friendly and all these factors that contribute to that. So we look into the whole process and then pick the scientific principles out of certain steps in that, yeah? So we look into this. And the thing we're going to look into is the ceramic capacitor. Of course, nowadays the next evolution of this is then the supercapacitor, but the capacitor is also still in use and fabricated in actually large quantities every year more, because we have more electronic devices that are power hungry. So, ceramic capacitor. And especially I should say, we're talking about a multi-layer ceramic capacitor. And that means acronym is actually MLCC. And why do we do this? So first of all, what is a capacitor? So you have electrodes, this in black, and you have a medium in between, and then you apply a voltage to the system and you develop charges on it. And of course, the opposite side will get then the opposite charge. The typical thing in the beginning when people developed this was in air, having two spheres and so on. And so what they found is when you work with planar systems like this here, then there's a relationship between the amount of charge that you can store on it and the distance of the gap. The smaller the distance, the more you can put on. But of course, and another thing is the higher the voltage, because the more the energy the charge has, the more can you pack on. The problem then is, of course, if you do this in air, so if this medium here is air, not a material, you get the electric breakdown of air, spark, the whole thing is discharged, doesn't work. So what can you do now to increase the amount of energy stored? You can, of course, then put in a material in between that does something and basically is being polarized. So you have then small, charges here on each side. So you have basically polarization, and therefore you can store more charge. Or you can also avoid dielectric breakdown. Yeah? So these are the two things. And what people discover then, if you work with ceramic materials that you put in between two metal plates, then you can come to really high capacities for these to high capacitance for the capacitors here. So how do these things then look like? For multi-layer, of course, you have basically a process where you make thin metal layers. I'm just drawing here a few now. And in between, you put a ceramic material. And many times it's also on the outside. Okay, oh, this is a little too far. I need to have these things available for contacts. And then, of course, you have to put in contacts so that these things are connectable. And you put basically everything here on a whole metal contact. Same thing here. You dip it, so you're not connecting to this here, of course. You dip this here, and then you have a metal contact here as well. Let me make this clear that not all of them are connected here. So this ends here. Yeah. So basically, each 2 layers are connected to the left side, 2 are connected to the right side. And yeah, of course, as I told you, the thinner the layers, the more charge you can put on, and that means we need to work on the thickness of these layers. So originally, people start to work because this is a ceramic material. You don't want to have electrical conductivity, and you want to have this high dielectric constant that is needed to increase the charge in the system. And yeah, do you know why we end up with ceramics and not with polymers for such systems? Do you have any suggestion? So, I mean, it would be nice if we can do this with polymers. And there are a lot of capacitors out there where people use a piece of paper in between, a plastic sheet in between. They're also available. But why don't we build capacitors that are most powerful like that? What is the fundamental property of exactly dielectric properties of the material, and the dielectric constants for plastics are not very high. Yeah? So for ceramics, you can go much higher, and especially the ceramics like perovskites, they have really high dielectric constants. They can go into the several thousands, even 200,000. But that is then very limited for certain frequencies, certain temperatures. So practical application, you can still go to 5,000, which means you can store 5,000 times as much energy as with air, basically, in the system. So that's why we end up with ceramics. So ceramics have the disadvantage we can't melt process them in such conditions because the melting temperature would be way too high for most materials to have as a port. The same thing is this electrode here is a metal. Metals melt typically much earlier, so you could do metals here like nickel is being used. There's of course silver, copper, and so on in use as well. And these melt around 1,000 Celsius typically, a little bit above depending on the material. And the ceramic wouldn't melt at the time, so you wouldn't be able to melt cast, so you have to go through a different processing technique. So automatically you end up with particles. And yeah, so we need to basically look into the processing for the whole system. Let's just do all the steps for this. So the first step overall is production. The first thing is we do a slurry, yeah, slurry preparation. That's a key thing because we work with particles, and there's actually 2 types of slurries. One is an ink that you have to do for making the paste here to print. So it's also a type of slurry, just higher viscosities. But the slurry preparation is pretty much for these powders here. Then on this slurry preparation, you follow up with a process. There are varieties of this, but one of them would be tape casting. That would be the older variety. And we're coming also to new varieties of this, what we do nowadays, in order to shrink diameters of these layers. So slurry preparation, tape casting, and after tape casting, we need to, of course, put them in a proper size. So it's called cutting. Because tape casting makes very large sheets, so you have to cut them. And then ink printing, yeah, so ink It's called screen printing. Screen printing of metal layer. And then, of course, you have just this one sheet, so you need to do it for many sheets. So you have a next thing then here, stacking. And you also need to do something else. You need to laminate them because the stack should stick together. And after that, you need, again, to cut these things into single units. Cutting, and then after cutting, you need to burn out the organics. And you have to then make the system dense, else you have electrical breakdown or lack of electrical conductivity. So we go through a so-called sintering process. And then, a last step is then, so we had to put electrodes on, so this would be called termination. And again, this is a paste that you put on, you have to heat treat it. You can also call this sintering again. Okay, so these are the steps for making such materials. And each of these steps requires quite some knowledge. And what we're going to do today is focus on this first part because there's a lot of fundamental science in there that can be applied towards any of the particle systems. And this also applies to if you make battery electrodes. It applies if you work with metal powders, because also in metallurgy you use powder metallurgical processes. So it's a wide variety of applications that you can use these systems for. So what do we do here in the slurry preparation step? And let's go here now. Okay. So what do you think is in a slurry? What do we put in there? Do you have any suggestions? What could be in a slurry? So one thing is, of course, ceramic powder. This is the first item, obviously. So what else is in a slurry? I mean, it's binder, okay. So that's a good thing, yeah. People put in binder. And what else? Solvent, yeah. Solvent, if you said the word binder, I agree to the word solvent, but you don't want to dissolve the ceramic powder. So the better term is actually dispersing aid, yeah, or dispersing medium. But some people refer to it as solvent. It's just solvent dissolves everything, which means your ceramic powder would end up as ions in solution, and that would be not good because the volume change would be too dramatic from solution to a solid, dense body in the end. So it's not feasible. Okay, what else is most likely in there? Do you have a suggestion what else could be in there? Maybe let's talk about this. You said binder. So what is a binder? What could this be? Is this a ceramic? It's a metal? Is it a polymer? A polymer. Okay, very good. Polymer. So what are fundamental properties of polymers that might be important for this? So obviously it's a mechanical property that we're interested in. That's why you add the polymer. Yeah, binder is supposed to hold the particles together in tape casting, in the dry state, not in the wet state. And when they hold the particles together, obviously you want flexibility of the tape. You want the tape to be, you can handle it. You actually, these materials are being handled pretty rough sometimes. You want to be able to drop it and it's still one piece. So what mechanical property is then really important for the binder? Adhesive. Yeah, adhesive, not adhering to the particles. That's a different story. But that has something also to build a certain quality of the tape. But the polymer itself, without particles, is also the mechanical property is important. So polymers have a variety of properties, in mechanical properties, depending on temperature. Yeah. So if you go to high temperature for polymers, which is in the range of 200 to 300 Celsius, and we're talking about thermoplastic materials, then they soften and even melt if it's a crystalline polymer. If you go to a lower temperature range, then they start to be leather hard, rubbery, and so on. And there's a glass transition temperature in there. And then, of course, at some point, when you're below the glass transition temperature, then they turn out to be very brittle. So you want to avoid that they're brittle. Of course, now you can't control the temperature too much. You typically work at room temperature. What can you do to basically change the glass transition temperature of the polymer? So you don't have the possibility to work at 50 Celsius or 100 Celsius, where the polymer would be above glass transition and therefore flexible and tough. So what do you do then? An additive, yeah, very good. But not a ceramic additive. What type of additive is it then? What property does an additive have to provide that it's lowering the TG for a polymer? TG means the chains start to be able to move freely. Yeah? If you below the system is frozen, you can't really move each chain segment. And above TG, now the segments have freedom to move around. So if a system is frozen and you want to be able to provide space to move, what do? You expand the volume of it. And how do you do this? You just add a solvent. Yeah? A solvent that is really liked by the polymer. And of course, you do this already when you use a dispersing medium, which is a solvent for this. But of course, in the dry state, that solvent is gone. So what other property is important for such a solvent? It must have a really, really high boiling point, which means a very low vapor pressure. And these solvents are then given a special name. What could they be called? A solvent that is in the polymer, stays there for a long time, for tens of years, because it's a low vapor pressure. It's very trivial. You're working with plastics. And they're called plasticizers. Yeah? So plasticizer is nothing else but a solvent that allows chain mobility. So it's a really good solvent for your polymer. But the solvent has a very low vapor pressure. So typically the boiling point for such solvent is around 300 Celsius. Yeah? So we need a plasticizer. Which is a high temperature solvent, high temperature boiling solvent for polymer, for binder. Yeah? Okay, so what else do we need? Because if you just take these ingredients, you most likely get not tapes that are satisfactory for production. There's something else needed. So a hint, so we use ceramic powder and we use a dispersing medium. But what does a ceramic powder most likely not do yet, even though we have a dispersing medium or a solvent? When you take powder, put it into a liquid, does it automatically disperse? No. So you have to do something about it. So what do you do typically? Yeah, yes, stirring. Okay, you put in energy. Mixing, stirring is many times not enough. So you go actually to more energy like ball milling, which is more like a mixing procedure, not so much grinding. So that is not enough typically still because these powders re-agglomerate. So what do you add then in order to avoid this? Dispersant, yes. Very good. So now we finally have a list of ingredients that at least you can make a tape. This is not the complete list what is used in industry because you have other demands in industry. In industry it's also required that you make a tape and you can store it for 12 months or longer, and it shouldn't grow mold, it should not decay in any way, so you actually have to put in other chemicals that protect basically from growth of mold and so on. And yeah, so we have now a list of what's in the system, and I can give you a little bit what people use in the industry. You have about, and this is volume percent, about 28 volume percent of the ceramic powder is in there. You have, what is this here? About yeah, 7% of this, and we have dispersant. Oh, so not dispersant. Dispersant is about 1.7%. Oh, sorry. It's this is weight percent, not solar. So weight percent. So 1.7% in weight. Dispersing medium is let's see, binder is about 7%. Dispersing medium is around 40%. And let's see what's missing then. Let's make this 2%, and it's more easy to add up. 30, yeah, and a plasticizer on the order of about 10%. Actually, this is a little higher. This is about 46%. So the rest is basically the plasticizer, which is also about a solvent, yeah? Okay, so you see there's actually not too much ceramic powder in the system. And I think, sorry, it's really, this is volume percent, not weight. This is volume percent. So by weight percent, this is actually dramatic because typically use barium titanate or strontium titanate as a powder. And these compounds are very high density, so compared to the other compounds, it's in mass, it's actually a lot. But you see in volume, it's actually not a lot of volume in the system. And you, yeah, have to be able to make from such a low density really dense systems later on. Of course, what disappears is this part. It evaporates completely, so you actually move to much higher densities of the ceramic powder. So let's see. What did people typically do before in the slurry preparation? So it's like barium titanate slurry preparation. And so you have to put in barium titanate powder, of course. What particle size do you think they used before? Yeah, but let's say 20 years ago, 10 years ago. So it's typically in the 10 micron range to 1 micron. And nowadays, of course, they're moving towards, or they're working with 15 nanometers. And many times, of course, they have to go away from this process and now use other techniques like salt shale, PVD, CVD processes. Yeah. So they had really large particles at the beginning. They're shrinking. So the surface dominates more and more the process. So you have to actually pay a lot of attention to surface science. So the old-fashioned system was then the dispersing medium was an organic compound. And why do you think they didn't want to work with water? Why do you think they put in this in organic solvents? And the solvents are typically methyl ethyl ketone, MEK, and ethanol, for example. Ethanol, ETOH, many times acronym. So why do you think people did prefer a methyl ethyl ketone and ethanol mixture and not, why don't they work just in water, which would have been easier? Because this one is flammable, this one's flammable, so it's not so easy to work with. So you have to have explosion protective equipment and so on. What do you think would happen when you put barium titanate in water? Come on, it's a ceramic material. If you put rock salt in water, what do you expect? It dissolves. Yeah? So sodium chloride dissolves in water. So barium titanate is also reacting with water. It's not completely inert. There's no ceramic that is completely inert. They always have a chemical equilibrium with the environment. Of course, sometimes it's really slow to move towards this equilibrium. And so what's the ceramic compound with the lowest solubility that we know in the universe? And we're talking about binary, not the larger ones. It's zirconium dioxide, yeah? Zirconia, it's solubility in water of 10 to minus 18 mole per liter. But you see, 10 to minus 18 mole per liter is not zero, yeah? So, of course, rock salt is on the several mole per liter, so it's a big difference. But things are soluble, and barium titanate is soluble in water, and so the compound reacts with water slowly. It doesn't dissolve completely, but it changes its properties, and that's why people stay away from it. Yeah? Okay, and we come back to this, because so in the beginning people used these organic solvents. The advantage here now is you don't dissolve the powder, so you stay with the same surface chemistry. The next thing is they dump in something they didn't understand quite why, and that is called a dispersant that we had here. So the dispersant was Menhaden fish oil. So what do you think that is when it's called Menhaden fish oil? Do you have any idea what this could be? Is it really from fish? Or is it something else? So Menhaden is really the name of a fish. And if you watch any of the storm right now that develops in the United States, that's where it lives. So if you look at the contour of the United States, the East Coast, something like that, Long Island up here and so on, and then Florida down here. The fish Menhaden doesn't taste really well, and so it's caught in large amounts and used for cosmetics industry, leather industry, paint industry, and so on. So they extract the oils from this, and the fish before that lived basically here along the coast. And in the 1970s, they were in such an abundance that basically the whole group of the fish lasted. I need another color. Basically, this was one group that swam up and down. So it was gigantic. So when you went out there, you didn't know what to do with that fish. Now, of course, it's so overfished there's actually a little bit concern that there might not be enough of that. So, we know now it's for sure fish oil. It's coming from the menhaden, something that doesn't taste so well, but provides really high quality oils. And how did this end up in making ceramics, in making basically capacitors? Do you have any suggestion how this could come in there? Why did anyone think of that this could be a dispersant? So the overall thing is these things don't develop necessarily in one field, so they come actually, people work across fields. So oils, especially drying oils, are being used for paint. That's how you develop paint. And of course paint was available for many centuries, yes, and people used linseed oil and other drying oils, and of course also fish oil, which is really nicely drying. But of course, I have to say, fish oil is highly purified, so it doesn't smell like fish. So when you go into a house that uses paint where fish oil is in there, it doesn't smell like decaying sea creatures. So, yeah, but this compound was basically used in making paint. And if you look into tape casting, it's actually very similar to making a paint thin film. That's why people thought about it, used it, and then okay, let's try it, and they found it worked. We come to this also, why it works. It's much more complex than just thinking about paint. So the next thing is we have dispersing medium, a binder. Is typically a polyvinyl butyryl, PVB. And yeah, plasticizer for this. There are several out there. That plasticized PVB, that's octyl phthalate. So this is a boiling point around 300 Celsius. Basically, it's a liquid at room temperature, and that dissolves well in the PVB. So now we have a composition what you can put in. Let's look a little bit what all of these things do in a slurry that affects the impact of the system later on. So menthane fish oil is actually a special compound that has been heat treated in copper kettles for several days. Auto-oxidation reaction has been done. So this one is a compound that has a broad molecular weight distribution. So it's not just a low molecular weight compound. This one here is typically, let's write it down, so molecular weight. From 1,000 to 150,000. And here, molecular weight is around 150,000. This one is, of course, a liquid. This one is a liquid. Yeah? So, how do these things work now? In order to make a slurry, you have to follow exactly a procedure. It's a hierarchical structure that you build, and it's therefore a correct procedure that you have to follow into making these things. So what you're doing, and that has been studied basically in detail, what happens there, you have your barium titanate particles. You add some of the dispersant, dissolve in some of the medium, and put it in a ball mill, so you grind it. So that means now that the dispersant that is in there adsorbs on the surface and protects the particles from reagglomerating. Yeah? So now you have some dispersing medium left over where you dissolve the PVB as a polymer, and you add this together with a plasticizer in the second step. So after you basically form this, now you add the second one, and I use now a black color for this one here, and then you basically get binder sitting all around. Yeah? So this means you develop a specific hierarchy, and this has been studied. If you do this what other people say, okay, let's just add everything at once. When you add everything at once, what happens? You get basically, this is a sequence, yeah? This is sequential addition. So, all at once. What happens when you add these things all at once? You come to this condition that you have a competition of compounds moving towards the surface. And this is a polymer, this is a polymer. So the diffusion rates are about similar. This can bond to the surface of the particle. This can bond to the surface of the particle. So what you end up with is sometimes like this, some spot like this, another one like this, and so on. Yeah. So the whole thing is in a mixed structure here, and it doesn't have to be even. It's just random distribution of these compounds. Yeah. And if you do the opposite, if you say, oh, I don't care what's the dispersant, what's the binder, you end up with such a structure. You have basically a binder molecule sitting on there. And then when you add the dispersant, it's a little bit out here. So when you now look at these structures that you build by adding them in the proper sequence, you will find then that this structure will be the most compact. This is for several reasons. One thing is that this compound has groups that can anchor strongly on the surface, so the chain is actually flattened. So it's, even though it's a high molecular weight, up to 150,000, similar like the binder, but it's not in a big coil. It's actually pulled down, and it covers the surface really nicely, but still has enough tails to stand out for giving dispersion. If you and then you add binder on the outside. The binder interacts, of course, with this, and now the binder can bind between particles, so you have actually the best conditions of everything. If you go for this system, it disperses it somewhat, but the viscosity gets really high because this binder interacts with other binder, chain entanglement, and therefore it's the viscosity is super high. You have to add a lot of more dispersing medium to make it thinner, and therefore you go to a really poor product quality. And the dispersant here doesn't do too much in helping. It's just actually deteriorating properties. So you could also leave out the dispersing medium then and process it, but it's still, the viscosity would be way too high. And if you reverse the sequence, then you end up now with the fish oil being the binder in between these particles, and that doesn't work because fish oil is actually a nicely repulsive system overall due to the side chains it has, and you still have plasticizer available that is a final solvent. So the mechanical properties are really poor, and PVB is not a good dispersant because it adsorbs in a coil in such a system that gives you too voluminous particles, basically. The particles take up too much space, therefore you have too high of a viscosity for this reason. So these systems can be observed, and this one is the system you really want. So the sequence is really important. So that tells us also something now, if we want to move towards aqueous processing, what we have to watch out for. So you have to also be careful what structure you build, basically like an onion shell system that you can build out there, and how large these structures are. And that's what we're going to look into next. So we're going to move into water. So we build aqueous systems, And before we do this, we have to look into a little bit what problems we expect. And it's very obvious when you look at the perovskite structure what could happen there. So perovskite is a unit cell where you have different possibilities, but I draw this now with titanium atoms in the corner. So you have titaniums here in the corner. And of course there's another one back here. And let's draw the others. Then we have a barium or strontium, whatever you want, here in the center. And we have oxygens on all the edges here. Also here. Yeah? Okay. So now if you just take the system and look at the top layer, you see there's actually no strontium or no barium exposed to the outside in this 100 layer. And only if you cut the unit cell lower, now you have a pure strontium oxide or barium oxide layer exposed. And again, if you cut down here, you have this layer exposed. And you can do several other cuts with the cell. You can go diagonally, then you have a strontium titanate layer exposed, and so on. The interesting thing is now that when you synthesize crystals and you grind them, then you break surfaces open. And that means now you will expose sometimes titanium oxide layers, sometimes barium oxide, strontium oxide layers, depending which one compound you use there. And that means the surfaces here will be either by barium oxide rich or titanium oxide rich. And when you put these things in water, we find that barium has quite some solubility, not so much titania. So barium solubility is rather large. And that means always when you process these materials in water, you actually mainly interact with the pure surface of titanium dioxide plus barium ions or strontium ions in the liquid. And let's have a short look into this, what it means. Let's see, didn't I bring the... Yeah, here's a phase diagram. So we now want to look into what happens with this compound when you put it into water. And that's basically the phase stability diagram. So what we plot here is the pH. And we do this from 0 up to 14. That's the maximum you can have in water. And here's the concentration of barium ions. And the concentration is typically, we have to do this in the log scale because it's so many orders of magnitude that increase. So you have here 10 to basically 1 mole per liter, so 0. Then here 1, so let's say -2, -4, -6, -8. And let's see, pH, of course, here is then half is 7. Here would be then about this would be 10. And this one here, same thing. This would be about 1, 2, 3, 4, 5. We need another one here. 6, 7. Okay, so we have here pH 6, 3. Okay, and before. So when we look into this, you can calculate it from some stability. There's thermodynamic functions. You can calculate equilibrium constants for solubility of barium ions in water depending on pH. And pH 14 is the maximum here. We cap it also up here at this level. And you find then that above pH 11.5 up to concentration of 10 to minus 4, you have barium hydroxide as the species in here. Then above that, a little bit like this, the curve, you have here barium titanate. And there's another line going down like this here. Yeah? So, and here else you have barium 2 plus titania. Yeah? So that means if you want to process this compound in water, and strontium titanate is rather similar. So if you want to process these compounds in water, you see actually you will start to leach out some of these, and it's called an incongruent dissolution reaction. So you actually move protons into the lattice, and you move barium ions out. So electric neutrality is there in the solution. And the top layers of your barium titanate is basically depleted. If you wait for years, theoretically, you see the phase diagram here, you would end up in pure barium and in pure titania. But we don't wait years. We typically process within a few days or hours, and therefore we have actually limits. So what they investigated is actually when you do this and you have a particle, it's about 5 nanometers, here 5 nanometer, where the depletion zone is of here's basically titania, and here's barium titanate. Yeah? So about 5 nanometers thick layer is where this depletion happens, but still it's a 5 nanometers out here that change the properties. Okay, so within the normal time frames, you basically have nothing stable. This would be the stable region. Why don't we process with a lot of barium ions in solution at pH 13? Why don't we do that? Do you have any suggestion? So that we find in water you can process it, you just have to go here to pH 13 and dissolve like 10 to minus 4 mole per liter barium ions. Do you have a suggestion why we don't do that? Why is industry shying away from working with pH 13? What happens when pH 13 splashes in your eyes? Any suggestion? When you get base in your eye, what do you do in the lab? What? You're not using acid after that, yeah. So when you splash really strong base like pH 13 in your eye, you wash it, yeah, okay. That's really dangerous. You have to wash it immediately and really strongly with the eye flushing station. But what is the problem? Why is the base so dangerous for your eyes? More dangerous than an acid. You probably heard your body's made up of proteins. What do proteins do when they come in acid or base? And that changed the solubility, basically. And base coagulates your proteins. So if you put base in your eye, it basically makes your lens system, your cornea, is turning milky white. So it's not about that it etches and attacks it. It's about precipitating proteins. So it's a really, really bad thing. Yeah. What else is there? So you don't want to work at this pH because if there's a spill, it's really difficult. And of course, it's possible to work at this. There are companies out there who work super caustic. If you make alumina out of bauxite, you work with extremes. But if possible, you want to avoid it. And if there's a smart way to avoid it, you do. Yeah? So the worker safety is one thing. What other thing is there? Why are you a little bit concerned to use barium at that pH? What else would there be? Have you ever gone to a store and bought rat poison? Yeah. So what could be in rat poison? Barium, yes. Barium carbonate is rat poison. So you're working basically with rat poison under very caustic conditions. Something also people are afraid of in large quantities. If you work in the lab, make a few milligrams, no one will die from that. And you make it in a safe condition so it doesn't spill. But if you have now large quantities, you have to be concerned. For example, hurricane. The roof is blown off, the whole batch runs out in the river, all fish dies, or it's not killing rats only, it kills a lot more things. The pH will also deteriorate things. Yeah, so if there's an accident, if you have large quantities, that's something of concern. And I don't know the number of tapes nowadays, but tape casting just for capacitors, the barium titanate, produced in 1992 a length of tapes that reaches from the Earth to the Moon. Yeah, it's gigantic lengths that are being tape cast. And so you see, if you have a production facility in some spot, you have to be concerned if there are large quantities of toxic compounds that can come out. Yeah? So that's why you want to devise a process where you don't run into this problem. Okay, luckily, there's one compound helping us a little bit, and that's when we breathe, carbon dioxide. Carbon dioxide forms a salt with barium. It's barium carbonate, which is actually the rat poison that we use. So barium carbonate is a solid, and you can actually precipitate some of the barium, and so you get actually here, actually a little further over. So it starts at 4, something like this. Yeah? This is the barium carbonate stable region. That would mean if you put barium titanate into water at pH 7, what will happen is you dissolve your barium ions and it reprecipitates on top as barium carbonate. Yeah? So for processing purposes now, you have a triple layer system. Yeah? Barium carbonate, titania, and barium titanate. Yeah? So you see already how complex a simple particle gets once you expose it to water. And that's why people like to work before always with non-aqueous systems. So now we have this compound. You know we have barium ions in there. And that's the part where we can look into a little bit how we process this material. So we work in water. We learned about van der Waals forces before. So barium titanate, unfortunately, has a very high Hamaker constant. So the attraction between particles in water is pretty large. The Hamaker constant is 80 septojoules. And that is, compared to a lot of other materials, like 10 orders of magnitude, 1 order of magnitude higher. So we need to do something to put repulsive potentials on there, and that's what we learned just in the last lectures, how to achieve repulsive potentials. Let me just put the equation down here again. So the repulsive potential that we need to achieve to overcome the van der Waals forces is then pretty much a, let's say I put something together in a constant here, make it constant, and yeah, let's look at this, what we can do. Just a few numbers here. So if you put barium titanate in water, and this is the window. You want to be pH 7, or let's say between this range 5 to 9 is a typical range that you want to work with. And if you look at this, you have always in the range of, yeah, you can actually have more, but in this range you have always easily certain amounts are available. So about pH 7, you actually at least 10 to minus 4 or 10 to minus 5 mole per liter barium ions. And let's use now equations that quantitatively describe that. And I need to plug this in, and hopefully it's getting to work. And I need to lower this. I guess this is the volume. No. Okay, I didn't press hard enough earlier. Can we turn the screen on now also? That is up, down, LCD projector. Is it on? LCD. Looks still dead. Ah, now it activated. Okay. You have to push the buttons twice here. Okay. Let's see whether we get this. So first of all, I need my computer. Let's see, is there a symbol on this one here? This one? Okay, this should be this one here. Okay, let's make this larger. And move this here. We need a sphere. Okay, so I showed you one equation here, and there's of course other equations that can tell about van der Waals interactions. And these are now programmed into the spreadsheet. And we can quantitatively predict nowadays what's going to happen. So what we need to put in is basic information for the van der Waals part. So the Hamaker constant. And you see the number is A132. That comes from historic, for historic reasons. Basically, you have material 1 interacting with material 2 with intermediate 3 in between, which is basically for us would be water. So we need to find the Hamaker constant, and some of them are published. One of them, here's a paper that I published on that, and barium titanate is in there, but there's also books now published from Adrian Pasichin and so on. So if you, it's also possible to calculate. There are programs available from Roger French. He has a program called Gecko, and with that you can put in the fundamental properties, dielectric constants, or any other thing you know about absorption spectra for your materials, and you can calculate your own Hamaker constants in case you don't know it. But many times you can look it up, and barium titanate here, for example, in vacuum, you would have a Hamaker constant from 18 times 10 to minus 20 joules. And as I said, for water, as you see, dielectric medium impacts the Hamaker constant. It's lower than in vacuum, but it's still substantial. So 8 times 10 to minus 20, or if you use septojoules, which is 10 to minus 21, it's 80. Yeah? So we put this number into this, and yeah, here you see, this is the key equation that we use to calculate the potential. So you have over the distance in here, and Hamaker constant times the radius basically of the system, of your particle. So we need to put in 80 into the spreadsheet. Or 8 times 10 to minus 20. That's correct. Okay, so let's chart 1. Let's see, is this the correct one? That's the, let's go back here. Let's put this at 0, 0. Yeah, that doesn't matter now. Okay, so that's the chart. And what you see here now is a plot. This is force. Let's go to another one that is easier to interpret. Let's see. KT, that's what I like, yeah. The only thing is I don't have the power to control the x-axis, the y-axis here. But let's discuss this. So when you look at this here, now we have we plot here the interaction energy between two particles. The particles are set according to the equation in there. We can modify that. And so we look now just at how two barium titanate particles interact with each other when they approach. And this is separation distance of the particles from the surfaces, and this is the interaction energy. And you see here we use the Boltzmann factor, K, Boltzmann constant times temperature, because that's a good description for the amount of energy the system has available. Do you remember what is the room temperature energy of molecules basically from this Boltzmann factor? Where are we at? That's why it's so exciting. You can basically evaluate systems based on this energy. It's 1.5 kT, yeah, 3/2 kT. It comes, if you can use the gas equations, basically derive the energy of a system from that by looking at the motion that is available and add it up. And so 3/2 kT is the energy. So if you look at such curves here now, you see this is a van der Waals attraction. It's negative. So 3/2 kT is basically contributing there as a positive energy. And if you were above here, this basically have repulsive forces. You're below 0, it's attractive. And 3/2 kT is pretty interesting because if you have an attraction that is weaker than 3/2 kT, that means the thermal motion of your system is able to kick the particles apart. So, but now you see here on the scale, 3/2 or minus 1.5 is somewhere up here, close to that. So this system is really strongly attracted. So you can't just use thermal energy to keep them apart. So we have to do something about that. And that is now here. So what we can do, we can put in some charge. And yeah, so right now also we can look. So we had a particle radius of 500 nanometers, 0.5 micron. Yeah? 500 nanometer is reasonable for older systems. The newer system we can do later on is, of course, much smaller. So we can have now the possibility to put a charge on the particle, and this now goes into the equation that we just had, the repulsive potential. So we have charge on one particle, and of course our particles are the same. So potential 1 and potential 2 are the same. So that will be something we can select. This is something we have to look into, and I showed you the diagram, so we can put in what is the concentration of the ion. The counter-ion valency is, we have to deselect, and because that compresses the repulsive force. So what do you think the counter-ion valency is in such a system? Or what is the counter-ion overall for that? Okay, let's say we take the barium titanate particle, put a positive charge on the surface. What is a counter-ion to a positive charge? It's something with a negative charge. Yeah, very good. So, if you have a positive charge system, your negative charge would be what? OH minus, chloride, Cl minus, or something like that, yeah? Okay. So, if your surface is negatively charged, what is the counter-ion? It's a cation, yeah? So basically a positive ion. Which positive ions are in solution? It's barium 2 plus, yeah? So divalent, yeah? That's why barium is really bad. It's divalent and does something to the system. Because you saw the last week, it's the square of this plays a big role. So let's put in 2. So we have a negative surface potential, and yeah, for equations it doesn't matter, so you don't have to write in minus and so on. So it's fine to just give the absolute value. So the potential will be then, let's say we put on 50 millivolts on each of the particles. And yeah, we have the temperature as room temperature. A little colder, so it's not 298, it's 293. So, and dielectric constant for the medium, that's water at 78.54. Yeah? So, let's see now. Everything should be calculated. And we want to look at this here now, yeah? Now you see the whole system changed. According to this, the van der Waals attraction, here this contribution disappeared. Let's go to the other one in KTs again, which was this one here. The van der Waals attraction is no longer dominating. So what you see here now is 2 things. So you have a little bit of an attraction here. That is basically so-called the secondary minimum. So the particles will be a little bit cohesive. So if you work with such systems, it will behave like some of the paints, which means when you let it sit, it becomes a solid. And when you apply shear forces, you can move the particles again. Another thing is, you have now here, there are 2 lines actually, because these equations have boundary conditions and you can solve them for 2 conditions. One would be you solve them with a constant charge on the system, or you solve them with a constant potential. And you see, if you use a constant charge, which is overestimating, because as soon as you approach things, you have not constant charge, because it's Le Chatelier's principle. If you have constant charge, you would mean you'll keep the concentration of compounds the same. If when you approach 2 surfaces, you can't keep it the same because the chemical equilibrium forces to have the back reaction. Yeah? Else you would have the high concentration in a spot. But total constant charge is one approach to do this. Another thing would be total constant potential, and that typically underestimates the system. So somewhere in between these 2 theoretical calculations, this will be your system. So you see, you get a really nice repulsive system, or at least a decent repulsive system, depending on this. So it's somewhere here. So the particles know of each other, are a little bit connected, but they're dispersed. You can keep them separate. So let's now change something here. And you saw this was actually a pretty high concentration already of the barium ions. So let's put in a lower concentration. And now you see, if you manage to go to below 10 to minus 4, the particles will no longer have the secondary minimum. They will no longer stick. Yeah? And even this barrier is now much higher. Yeah? So and this is now, you see also, we're far above the room temperature energy that the particles could bump over and coagulate. And let's play a little bit with this more. You can put in a lot of numbers. Let's say make it 25 only. And we put in here much more diluted system. If you can achieve something like this, then it's also nicely repulsive. Look, if you have a really low counter-ion concentration, it's beautifully repulsive. Yeah? It's only if you push particles over, then of course the primary minimum is there. But because, yeah, once you push them together, van der Waals forces are dominating. But once you separate them, they can't typically get together. And so you see, this concentration is really, really important. So you want to keep it as low as possible. And that's the big challenge that we have, because in our system, the barium ions compress this double layer. Typically, you are easily, and let's put in just other numbers here. 0.1 is easily possible. And look now at the chart. Yeah. So barium ion concentration really messes with you. So what can we do now to still process it in water? Because let's move this up, then you can this one here and up. No, wrong button. No. Yeah. So we can easily have a concentration of 10 to minus 2 or 10 to minus 1 mole per liter if you're in this range. And also I should say barium titanate is typically negatively charged in this pH range here. It's only when you go to much lower numbers that it's going to be positively charged. Yeah. So that's why we're stuck with this problem. So what do you think we can do to still process this in water despite the fact that charges don't work so well? Do you have any suggestions? What would you do as a scientist? And that's something we can maybe do a little bit other exercise. We still have 5 minutes, and we can make 2 groups here, basically 3 students and 2 students together, and discuss a few concepts. How would you overcome this problem? You want to do this electric double layer stabilization, and obviously you have to do something about either the barium ions or something else in the system that you can process it. So let's get together a little bit, and you can form the groups as you like, and you discuss a few solutions, and then we discuss one solution today and the rest of this tomorrow. Yeah. Okay. So just move. Two people have to move somewhere, so you're so closer together. You discuss with them? Okay. So yeah. So what ideas do you have to overcome the problem? Yeah, so I showed you in the calculation that when barium ions are present, that you cannot process this system in water. But we want to process in water because it's environmentally friendly, and you want to process around pH 7 and not on pH 14. So you have a real problem now. And that's why people didn't process barium titanate for a long time in water. But there are 3 solutions that you can propose, at least 3 that the industry came up with, that you can still process these materials in water, despite the fact that I just showed you if you just put it in water, it won't work. Yes, that's what I said. It's a demanding industry. You don't want to work. You have to think about you're working with tons of materials. And if you have a ton of material at pH 1 or at pH 14, if you can avoid it, you want to. It's just it's too dangerous. So you want to work for safety reasons around pH 7 as much as possible. And obviously, people are capable of doing it. You don't have to be in such extreme pH values. It's just you have to have clever ways of doing that. And this is the thing that whatever you do in other processes, you will have the same challenge. The window that you would like to work in is not necessarily where it's easy to work in. So you have to devise ways of coming up, making possible.
Those solutions, those clever ways, what are they related to? Because it's not related to the concentration, or not the change pH is about some other additives in water.
Yeah, okay, but you can say basically, what is it that you need to do to make it available to process? I mean, if you want to make an electric double layer stabilization, obviously you can't have barium ions. So what you need to do something about the barium ions. So you just come up with some idea what you can do with barium ions. And I'm not asking a specific solution, which compound you use or whatever, but propose general principles that could be used.
I would say, obviously, I mean, put something, add something that neutralizes barium ions.
Okay, cool. Yeah, so one solution would be solutions. So I would call it scavenge barium ions. Yeah, not necessarily. What do you mention? Yeah, so that would be an idea to basically steal them, pack them away in some way. Any other possibility? Okay. So I agree that's a clever idea, and that's actually what you can do. The question is then, of course, how, and that's something we can discuss then tomorrow in lecture. Yeah. What you can do is think a little bit about it yourself. How would you steal or scavenge, as it's called, and these ions away that they're not in solution anymore? What could you do? Yeah. Okay. With this, we close for today and continue then tomorrow. Thanks.